At 2 in the morning on a mountaintop in northern Chile, a machine the size of a small car swiveled toward the sky and did something no camera on Earth had ever done before. It opened its shutter for a fraction of a second, closed it, and in that instant captured more information than most telescopes gather in a week. Nobody in the room cheered. They just stared at the screen, because what came back wasn't a photograph. It was 500,000 galaxies, frozen mid-existence, packed into a single frame. Somewhere in that frame were objects whose light had been traveling since before the Earth had continents. And this was just one image. Out of more than 1,000, the same machine would take that same night, and the night after, and every night for the next 10 years. This is the Vera C. Rubin Observatory, and in the summer of 2026, it did something that made astronomers stop scrolling, stop arguing, and just watch. To understand why one telescope could do that, you have to go back to the woman it's named after, to a problem she stumbled into almost by accident 60 years ago. Vera Rubin wasn't trying to discover the biggest mystery in physics. In the 1960s and 70s, she was measuring how fast stars orbit the edges of spiral galaxies, expecting a simple, boring result. Stars near the center of a galaxy should whip around fast, pulled hard by all the mass packed in close. Stars near the edge should move slower, the same way Pluto crawls around the sun while Mercury races. That's how gravity is supposed to work. That's how it works everywhere else, in the universe we can see, except it didn't. When Rubin measured the outer stars, they weren't slowing down. They were moving at almost the same speed as the stars near the core, as if the entire galaxy were spinning like a solid disk instead of a loose spiral. There was only one explanation that held up. Something invisible was out there, wrapping every galaxy in a halo of mass with no light, no color, no signature except its gravity. Rubin hadn't just found a strange result. She had found the first solid evidence for what we now call dark matter, a substance that makes up roughly a quarter of everything in the universe and that, to this day, no instrument on Earth has ever directly detected. Rubin never won the Nobel Prize for it, an omission plenty of physicists still call one of the great injustices in the field. She spent decades afterward pushing for other women to get a fair shot at observatories that, when she started her career, sometimes didn't even have women's restrooms built into the design because nobody had planned for a woman to be looking through the eyepiece. By the time she died in 2016, she wasn't just known for a discovery. She was known for insisting over and over that the universe still had obvious things left to explain, if only someone built an instrument patient enough to look. So when the U.S. National Science Foundation and the Department of Energy set out to build a telescope engineered specifically to hunt for dark matter and its stranger cousin, dark energy, there was really only one name it could carry. The observatory sits at nearly 8,700 feet on Cerro Pachón, chosen for the same reason astronomers have prized the Chilean Andes for decades: dry air, dark skies, and some of the steadiest atmospheric conditions on the planet. But altitude and clear air aren't what make Rubin different. What makes it different is sitting behind its mirror, the largest digital camera ever built, a 3,200 megapixel sensor roughly the size of a small car, engineered to do something no previous survey telescope could manage. Most great observatories, like Hubble or Webb, are built to stare. You point them at one patch of sky, sometimes for days, and you go deep. Rubin was built to move. Every 40 seconds, it takes a new exposure, then swings its entire 8.5-ton mirror assembly to the next patch of sky, and does it again. Over a single night, it can photograph an area larger than 1,000 full moons. Over 10 years, that adds up to roughly 2 million images, and by some estimates, more than 500 petabytes of data, enough to make Rubin not just a telescope, but essentially a real-time recording of the entire visible universe, replayed every few nights like a movie. Building a machine like that took longer than building the telescope itself. The camera alone required custom sensors, sensitive enough to register a single photon of light that left its source billions of years ago, mounted on a structure rigid enough to survive being swung across the sky thousands of times a night without so much as a micron of misalignment. The data pipeline needed to process that flood of images had to be built almost from scratch, because nothing that existed before Rubin had ever been asked to compare 1,000 new images against a growing archive of millions every single night, and flag anything that changed within minutes. That processing backbone now lives at the U.S. Data Facility, hosted at SLAC, National Accelerator Laboratory, which also coordinates with the Dark Energy Science Collaboration, a worldwide group of researchers who will spend the coming decade mining Rubin's numbers for the faint statistical signatures that no single image could ever reveal on its own. The project first showed the world what it could do in June of 2025. In just over 10 hours of test observations, cobbled together from images nobody expected to be spectacular, Rubin's engineers released a preview that stunned even people inside the project. In that short window, the observatory had already logged millions of stars and galaxies and discovered more than 2,000 previously unknown asteroids, 7 of them passing near Earth. To put that number in context, all the world's other ground and space telescopes combined typically find about 20,000 new asteroids in an entire year. Rubin found over 2,000 in half a day, without even trying, during what was essentially a warm-up. That was the appetizer. The real survey, the one this telescope was actually built for, didn't start until more than a year later. Getting there took longer than the project's own scientists hoped. The observatory's leadership had originally aimed for an early 2026 start, but as Director Jellico Ivizic explained when the delay came up, the team wanted to be certain about image quality, survey speed, system reliability, and calibration accuracy before committing to a 10-year clock that couldn't be paused once it started. So the checkouts continued through the winter and into spring, engineers stress testing every part of the system that would soon be running unattended, night after night, for a decade. Then, on June 30th, 2026, it began. The Legacy Survey of Space and Time, LSST for short, officially went live. The name undersells what actually happens. This isn't a survey in the sense of a one-time catalog. It's designed to scan almost the entire visible southern sky roughly every 3 to 4 nights, generating what astronomers call the deepest, widest, fastest movie of the universe ever attempted. And because Rubin doesn't just take pictures, it compares them. Every new image is checked against everything the telescope has already seen, and when something has changed, brightened, dimmed, or moved, the system flags it within minutes. In February 2026, months before the full survey even launched, Rubin issued its first automated alerts from the system, a milestone the observatory called the start of a new era of dynamic astronomy. Once the full survey ramped up, that alert stream was projected to reach roughly 7 million notifications a night. 7 million times a night, somewhere in the visible universe, something changes, and Rubin notices before almost anyone else does. That capability turned out to matter almost immediately, in a way nobody had specifically planned for. During its commissioning phase, while engineers were still calibrating the system, Rubin happened to be pointed in the right direction at the right time to catch something extraordinary passing through our solar system. 3I Atlas, only the third interstellar object ever confirmed, a visitor from beyond our sun's gravity that will pass through once and never return. Between late June and mid-July of last year, Rubin caught it repeatedly, sometimes deliberately, sometimes by pure chance, because the object happened to drift through a patch of sky the telescope was already scanning. Researchers led by Colin Orion Chandler later used those incidental observations to measure the comet's orbit, its structure, and its faint surrounding coma. The fuzzy envelope of gas and dust that forms as ice on the object's surface begins to sublimate in sunlight. It was, in effect, a preview of exactly what Rubin is built to do at scale. Not just observe the universe, but catch the fleeting, unrepeatable moments that other telescopes would simply miss. Then came August. On the 7th of the month, Rubin released what it called Early Data Preview 2, its first major science image built entirely from data captured by the operational LSST camera, rather than earlier test runs. The target was the Cosmos field, a patch of sky several times larger than the full moon that astronomers have prized for years, precisely because it's unusually free of bright foreground stars from our own galaxy. That emptiness up close is what makes it so crowded far away. With the clutter removed, Rubin's image revealed more than 500,000 galaxies in a single frame. Spirals, with delicate arms caught mid-rotation, smooth, featureless ellipticals, galaxies visibly warped and merging with their neighbors, and faint red smudges that are some of the most distant objects ever captured by the observatory. Their light, having traveled for billions of years before finally landing on a mirror in the Chilean Andes. It's this image, and the flood of scientific catalog data released alongside it, that astronomers online started calling the moment Rubin stopped the world. Because for a few days, an unusually large share of the astronomy community simply paused whatever they were working on to look at it. Here's why that pause mattered. A single beautiful image is nice, but it isn't science on its own. What made the Cosmos release significant is that it wasn't a one-off. Rubin will return to this exact patch of sky every couple of days for the next 10 years, layering observation on top of observation, building a genuinely dynamic view of how that section of the universe changes over time. Combine that with the telescope's core mission, hunting for the gravitational fingerprints of dark matter and mapping how galaxies cluster across cosmic time, and you start to see the actual target Rubin is circling. This is the same fundamental mystery Vera Rubin identified in the 1970s. Dark matter's invisible pull, paired now with its stranger sibling, dark energy, the unexplained force that appears to be accelerating the universe's expansion. Just weeks before the Cosmos release, the Dark Energy Survey collaboration, working with data from the DOE-built dark energy camera on a separate Chilean telescope, published a 6-year analysis that tightened our constraints on the universe's expansion history by a factor of 2 compared to earlier work. Rubin is designed to make that kind of leap look routine, because instead of one collaboration compiling 6 years of carefully stitched observations, Rubin generates that density of data roughly every few nights. The asteroid numbers alone hint at what 10 full years of this might look like. Rubin's own team has projected that within the first 2 years of the complete survey, the observatory should discover millions of new asteroids in our own solar system, dwarfing the combined output of every other observatory on Earth. Most of those objects posed no threat to anyone. A handful, the ones that cross uncomfortably close to Earth's orbit, are exactly the kind of thing planetary defense researchers most want an early warning about. And Rubin's 40-second cadence means those warnings could arrive years earlier than they otherwise would. There are, to be fair, limits to how far the story can be pushed right now. Rubin has not detected dark matter directly, and it isn't designed to. No instrument has. What it does is map the gravitational evidence at a scale and precision no previous survey could match, which is exactly the kind of evidence Vera Rubin herself once used to argue that dark matter existed in the first place. The current data release, EDP2, is also explicitly a preview. A second phase, expected sometime between October and December of 2026, will add further processed data drawn from Rubin's individual exposures rather than combined images, deepening the picture rather than completing it. And the survey itself is barely out of its first year of full operations, a small fraction of the 10 years it's contracted to run. What Rubin has shown so far is less a finished discovery and more a demonstration of pace, proof that a machine built to move fast, watch constantly, and never blink can surface in months what used to take other observatories the better part of a decade. That's the real weight behind the phrase people have been using online. Rubin didn't stop the world because it found one shocking answer. It stopped the world because it revealed in a single image and a single data drop just how fast the answers are now going to arrive. Every 3 or 4 nights, the same patch of sky comes back into view, a little more resolved, a little more complete, folding into a 10-year time lapse that no human being has ever had access to before. Somewhere in those millions of images still to come are supernovae caught in their first hours. Asteroids that would otherwise have gone unnoticed until they were uncomfortably close, and quite possibly the sharpest evidence yet for the invisible material Vera Rubin spent her career trying to prove was real. She never got to see this telescope switch on. She died in 2016, nearly a decade before the first test images came back from Cerro Pachón, and almost exactly a decade before the Cosmos field image that had astronomers online calling this the moment Rubin stopped the world, but every 40 seconds. In the dark and cold of the Chilean Andes, her name points at the sky and takes another picture of the very thing she spent her life insisting was there, patiently building the kind of evidence she once had to fight to get anyone to take seriously. If you want to see how far that idea has traveled since a skeptical young astronomer first plotted a strange curve on a piece of paper, keep watching this channel, because Rubin's 10-year story is only just getting started, and we'll be here for every data release along the way.